Hey everybody, welcome into lecture number 18 of the semester. This lecture is on spanning trees, and this lecture covers two sections of Rosen's text. So in Rosen's text, this covers sections 11.4 and 11.5. So let's get into it. Number one, let's first define what we mean by a spanning tree. So let's let G be a simple graph, and we'll define a spanning tree of G. So let G be a simple graph. A spanning tree of G is a subgraph of G that is a tree containing every vertex of G. So a spanning tree of G is a subgraph containing every vertex of G that is a tree. I'll say is also a tree. Okay, so let's start then by looking at a graph, a simple graph G, and trying to find a spanning tree. So I've got, as usual, a bunch of images down here. Here's one. So let's put this in context up here. Here's a graph. Let's try to find a spanning tree of this graph. Now, it turns out that there's more than one option. So there's more than one spanning tree of this graph. Number one, we just have to make this a tree, right? So what's one of the properties of a tree? A tree has a simple path between all vertices and no circuits, right? It has no circuits. So basically what we have to do is kind of eliminate a couple of edges here where there are circuits. So whenever we see a circuit, we can kind of eliminate an edge. And there's lots of ways to do that, right? So first of all, we see a circuit right here. We want to break this circuit. So we could break this circuit by getting rid of this edge right here, right? Then we see what? We've got another circuit down here, right? So maybe we want to break that circuit by getting rid of this edge. And then finally we have a circuit here, so maybe we want to get rid of this edge here. And then what would we be left with here? Our spanning tree would be something like this, right? But this is obviously not the only answer. There are other answers. We could have kept all three of these sides that we got rid of, right? And instead we could get rid of three different sides. So we could get rid of this one instead, this one instead. So that breaks that circuit, this breaks this circuit, and we could even get rid of, we want to use this one, right? So we can get rid of this one. And so another option here would be, in dark blue, this spanning tree right here. So there's at least two options, right? It turns out that for this graph there are four different options, and we can debate whether or not they're isomorphic or not. Clearly these ones, the magenta, if you can still see it, the magenta and the blue are not going to be isomorphic here, but let's see. So like I said, there's four different versions for this example, four different spanning trees, and here they are. So let's see which ones we got. I'll put this graph right here. This image, I should say. It's got four graphs, right? Four spanning trees. So which ones did we find? We found this one. This was our magenta. Actually, there's more than four, right? So there's at least four because we've got this magenta one. And then we also found another different one, right? So we found two more different spanning trees than there are here. So everything that we found, there's no simple circuits. We touched every vertex, right? So we found spanning trees as well. But look at, so there's lots of different versions here. So there's at least six then, because we found two more, right? So there's lots of different versions. So that shows that spanning trees are not going to be unique, right? They're not going to be unique objects. But however, we can always ensure that they exist under certain circumstances. So the next item that we want to talk about is an existence theorem. So again, we're not going to get uniqueness, right? Uniqueness means that there's only one answer to our spanning tree. There's going to be, in general, lots of different spanning trees for a given graph. But we can prove uniqueness. So here's our theorem. We're going to sketch the proof of this theorem. So this theorem states the following. A simple graph is connected if and only if it has a spanning tree. So a simple graph G is connected if and only if it has a spanning tree. And remember, if and only if goes both ways, right? So this, you could read this as a simple graph G has a spanning tree if it's connected, or only if and only if it's connected, right? So our example was connected, and it was simple. And how did we divide? How did we find the spanning tree? Well, we just removed edges from the circuits, right? So we removed edges from the circuits, and that's how the proof of this theorem is going to go, actually. So the sketch of the proof. Like when I say sketch, I don't mean a picture. I just mean an outline of the proof. So we'll prove both directions here. Let's first suppose that G is simple. So if we suppose G is simple and has a spanning tree, right? It has to be simple. So the theorem is about connected and spanning trees. So it has a spanning tree. All right. Now, what does that mean, right? So we want to prove that it's connected. So let's call the spanning tree T. Well, T contains every vertex of G. T is the spanning tree here, right? T contains every vertex of G. That's part of the definition up here, right? A spanning tree of G is a subgraph, we'll call it T, containing every vertex of G. That's also a tree, right? So it contains every vertex of G because it's a spanning tree. And because it's a tree, the definition of a tree says there is a simple path between every pair of vertices. All right, so since T is a tree, there is a simple path between every pair of vertices. Now, this is important because what does it mean to be connected? Well, connected means that there's a path between every pair of vertices. It doesn't have to be simple, right? And so therefore, this G must be connected. So this direction is very straightforward, right? So therefore, G must be or is connected. All right, so there's one direction. In the other direction, we have to assume or suppose that our graph is connected and try to argue that it must also have a spanning tree, right? So next, let's suppose that G is connected. All right, and it's still a simple graph. So we've assumed the simple. We're going to stick with the simple, right? So once we assume that G is connected, then there's two possibilities. Either G could be a tree, and in which case we're done, right? Or it's not a tree, right? So if G is a tree, there's nothing to prove. So let's just say if G is not a tree, then it must contain a simple circuit, right? Remember, that's part of the definition of a tree as well, right? That it doesn't contain a simple circuit. So if it's not a tree, then it does contain a simple circuit. It's a simple graph, right? So the simple circuit is kind of redundant here, but it's important, though, that it contains a circuit. So find one of those circuits, right, and remove an edge. So we can remove one edge from a simple circuit. Now, we're not removing the vertices, right? We're just removing the edge. This leaves the vertices. So I'm going to make a claim here that I want you guys to verify. But I claim that this graph is still connected because we have not gotten rid of the vertices, or of any vertices. We've just gotten rid of an edge. So claim the new graph, the subgraph, is still connected. All right. So basically, let's just draw a very, 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 very simple picture here. The simplest kind of simple circuit that you can have, right? So if this is a subgraph of our graph, a simple circuit, and we remove one of the edges. Now I drew a triangle, doesn't matter which one, right? Say I remove this edge, then the graph is still connected because there's still a path between any two vertices. So really, these are the two that we've removed the edge from, the single edge that connected them, right? But we can still get from one to the other by taking these two. So this is going to be true even for a more complex simple circuit. Once we believe this, right? We've made this statement and we believe it, then we can repeat this process until no simple circuits remain. So this process can be repeated, or iterated, you could say, until no simple circuits remain. And this is basically how we did this up here, right? How we did our construction on the first example. So no simple circuits remain. And so the resulting subgraph is going to be a tree after this process, right? With no simple circuits. All right, so there's a proof that connectedness and spanning trees are equivalent in some sense. So a graph being connected and having a spanning tree, those are equivalent, at least in this sense, right? Equivalent in the logical sense. They're obviously different definition. They mean different things, but it's an if and only if relationship here. All right, well, the rest of the lecture here is going to be algorithms on how to build spanning trees, okay? Build spanning trees given a graph. Now, we're going to do examples for graphs that are relatively small because we're trying to learn and make sure that we understand how these algorithms work. But in general, these are going to work, the whole idea is that these will work on giant graphs, very large graphs, and you can program a computer to do these for you. The basic ideas of this course, right? So the first algorithm is called the depth first search algorithm. All right, and this works as follows. So we start with a simple connected graph G. So let's let G be a simple connected graph. So we know by the theorem that since it's a simple connected graph, that the simple connected graph must have a spanning tree. We want to find it, okay? So what we're going to find is actually a rooted spanning tree. So all of the algorithms that we use from here on out are going to produce rooted trees, okay? So we'll produce, and this will be the same for the next algorithm at least, the next couple. We'll produce a rooted spanning tree. All right, well, anytime you want to find a rooted tree, the first step is to define a root, right? So we can choose any vertex to be the root. So choose an arbitrary, that just means any one of them, it doesn't matter how we choose it, an arbitrary vertex to be the root. All right, step 2 is from the root, form a path and make it as long as you possibly can. So no repeated edges and no simple circuits. So form the longest simple path possible. This is even saying it's the longest is arbitrary. I shouldn't say it this way actually, right? So let me say it this way. So form a path starting at the root, so the vertex that we've just chosen, and make it as long as you can. It doesn't have to be the longest path possible from the root, but form a path starting at the root where no edge repeats, obviously, and there are no simple circuits. And make this path as long as you possibly can. All right, so then the question is, once you get to the end of this longest path, this path that you've made as long as you can, if you're still not done, then you have to get the other vertices, right? So if the path does not pass through all vertices, you go back to the previous vertex, the first to last vertex, and try to extend it from that vertex in a different direction. And if you can't do that, you move back to the second to last vertex, etc. Okay, so if the path does not, or the tree at this point, does not pass through all vertices, go back one vertex and try to extend it. If this is not possible, go back further, right? So if not possible, go back to the previous vertex. And then this can be continued until you finish the whole tree. So continue until the whole tree, the whole spanning tree is formed. All right, so this is wordy. It's as usual. The best thing that we can do is do an example, right? So I've got an example. I've got an image here that I'd like to. I can't remember for this one if the image has the answer. Yeah, for this one it has the answer. So for this one, we'll just take a look at what the book has suggested, and then we can talk about if it's possible to do it differently. And of course it is, because the first step is to choose any vertex that you want, right? So here's the answer, one answer that the book gives for this example. So here's a graph G. The first thing that they do is choose the root. So they've chosen the root to be f. So here's our root f. And then it says, make a path and make it as long as you can, right? So in this case, the path that they've made as long as they can goes from f to G to H. So to G to H, and then over to K, and then up to J. Okay? So there's step B, they've called it, but there's the longest path that we could make in this direction, right? Okay, what if you had chosen to go to I? That's fine. What if you had chosen to go straight from F to H? That's fine as well. Because you don't really know how far you're going to be able to make it, especially in a very, very large graph where everything is intertwined until you get there. So you just go as far as you can, you get a portion, right? That's good. Now, what's the algorithm say to do? Well, we've reached an endpoint, so we go back to the previous vertex. Is there any other direction we could go from here? No. So then you go back even one more step to the previous vertex, H, and from there is something we can add, right? So that's where we add this portion right here to our tree. All right? Now, we go back. Now, everything on the right-hand side of our graph has been accounted for, right? So now we go back to the left-hand side, and we can see, what are we going to have to do? We're going to go D to E to C to A. So basically, again, this graph we can see how we should go. We get to C, and now you have a choice, and it doesn't matter which way you go. They chose to go to A, right? And from here, what do we do? Well, now there's still one more, right? So you go back to the previous vertex. You've reached the end of the road. Back to the previous vertex, you go out to B. And so the B, that's where this one comes from. And so there's a spanning tree obtained by the depth first search of G. All right, can we do better, or can we do it differently? Well, what if we choose a different root, right? That's the obvious first thing that we could do differently. What if we just choose A to be our root? We choose A. Well, from A, look what you can do. You can go A to C to E, right? A, C, E to D to F to G to H to K and then to L, right? So what have I done here? I've traveled, let me do it as a highlighter. I've gotten all of this as one branch, right? Now I need to get the other branches in here. So from here I can go, all right, if I just follow the algorithm, I reach J, that's the end. I have to go back to K, nothing I can do from there. Go back to H, from there I can go to I. So I'll add in this branch to my tree. All right, but that's it. That's a dead end. So then I go back until I get to C, and from C I can add in B. So this is also a spanning tree. This is a rooted spanning tree with a different root, but notice that the general shape of it's the same. It's just like this one's been folded out in some sense, right? And flipped around, I guess, but flipped around and folded out. But it's created the same tree, though. That's the idea. So we've got our spanning tree here. Okay, the next algorithm The next algorithm is called breadth first. So this is the exact opposite. You can probably guess how this is going to go. This one's called depth first because if we think of, especially if you think of your root A, we found a real long branch, right? A real long depth, a real deep branch. And then we went back and added sub-branches, right? The breadth first is going to add lots of branches, but they might be shorter. Okay, so this is going to be the breadth first algorithm. So I think we're on item 4 here. So breadth first search algorithm. Now, it's probably not really that useful for me to spend all my time writing and not talking on a video, so here's the basic idea. Choose a root again. Choose a root. And then, number 2, connect the root to all the adjacent edges. So connect branches to all adjacent edges, or adjacent vertices, I'm sorry, vertices. So you use the edges that are adjacent to get to the next vertex, but so to all adjacent vertices. And then 3, for each of those vertices, so for each vertex and the next step, right? At the next step, repeat this process, right? But just be sure not to make any closed circuits, right? So being sure not to form a circuit. And then repeat until the tree is done, right? Repeat until the spanning tree is complete. All right, so let's look at an example for this one. This one I think I just have a blank graph, and then I do have an image of what the book deems the solution, but let's do it our own way first, and then we can compare. Let's do it differently. Well, I mean, you guys don't know, but let's do it kind of in a semi-obvious way. Well, I mean, it doesn't matter. So let's just do it our own way. So the first step is to choose a root again, right? So the root that I'm going to choose doesn't matter. It really does not matter which vertex we choose to be a root. We can choose any one of these endpoints. We could choose A. Let's choose F, all right, to be the root. I'm going to put this one on top. And then from F, there are 4 branches that come out, right? So from F, what do I have? I have C, I have E, I have G, and I have J, right? And then from each one of these, I can continue out. So from G, I can only go to L, because J is already accounted for. From J, I can only go to I, right? But if I go to I, so here's L, here's I. From, if I go to I, if that's all I do, right? If all I do is go to I, sorry, if I go to I from J, then I can't go to I from E. So from E, I can go to B and to D. Kind of working in reverse order here. To B and to D. And then that's it, right? Because from C, I cannot get to B. B's already been accounted for. So C's done. C's a leaf. All right, so then I go to the next step, and I connect anything that's missing. So here I can go from I to K and to H. I go to everything that I possibly can. Why did I start with I? I don't know. I just did, right? So from K and to H. And where else can I go? I can go from B to A. C's already accounted for. D becomes a leaf. So B to A. And then there's one more thing that I need to account for. That's M. M, I can only get 2 from K, right? So there's a breadth first search that has created this tree. All right, if you can imagine these black edges not being there anymore. So you only use the blue, the orange, the magenta, and the green. Then you end up with this tree over here. And so this is a spanning tree for this graph They use the breadth first algorithm. Now the book did it differently. They use E as a starting vertex, as the root. So let's see how that changes things. But otherwise, they did it exactly as we did. So here's what they've done. They choose E first. And just like F, there are 4 branches off of E that are possible. E takes care of what? B, D, F, and I. And then they worked in order from there. So from B, you can take care of A and C. And then D, it only leaves H, right? From F, you can take care of G and J, because C's already been taken care of, right? And that only, then I, from I, you can get to K, right? From I, you can get down to K. And then from there, there's only these 2 kind of hangers on, M and L. And M and L have to get attached to G and K, respectively, right? So same idea. This one is more broad. The breadth is larger because of the choice of the root, right? But the choice that I made, F was far enough away from M that it had to be this far if you want F to be the root. And when you make that arbitrary choice of your root, you don't know what's going to happen, right? Especially in a very, very large graph. You don't know if you're choosing, the widest possible, the deepest possible. You're not really sure, right? So these are all, these are equivalent. Yeah. So let's leave that there. The next thing that we want to talk about are minimum spanning trees. So this is where it switches to section 11.5 in the text. And so minimum spanning trees, these are, the idea of being a minimum spanning tree is only for a rooted tree, because a spanning tree itself, if you have n vertices, like here, what would we have? 1, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 13 vertices in this graph. Vertices in this graph. This is going to have 12 edges. A spanning tree is always going to have n minus 1. If you have n vertices, it's going to have n minus 1 edges. So a minimum spanning tree is something that can only be discussed if you have weighted edges. So we'll start here with minimum spanning trees. We'll give the definition, and then there's 2 algorithms here, which we'll do separately. So the first one, so first of all, definition, right? Let's let G be a simple connected weighted graph. So again, simple, connected, and weighted edges. All right, a spanning tree, so a minimum spanning tree is a spanning tree for which the sum of the weights of the edges is the smallest. Exactly what you would think, right? So a minimum spanning tree is a tree for which the sums, it's a spanning tree. So it's a spanning tree of G for which the sums of the weights of the edges is minimum. All right. Well, I think that idea makes sense. There are 2 algorithms. This first one is called the Prim-Yarnik, or just Prim's algorithm. I'll give both people credit. So Prim-Yarnik, maybe, algorithm. This one says the following. The first thing that you do is you choose an edge with the smallest weight. So step 1. So we're going to build the tree, right? We're going to build the tree based on the edges because the edge weights are the things that we're trying to minimize. So we choose an edge. There could be more than one, but choose any one. Choose an edge with the smallest weight. All right, and then from there, from that edge, you add an edge of minimum weight to one of the incident to one of the vertices already in the tree. Okay, so add an edge of minimum weight to one of the vertices. There could be many at this point, right? I mean, at the first step, there's not going to be many. There's going to be two choices, two vertex choices, maybe multiple edge choices. But as you go along, you're going to repeat this process. So to one of the vertices in the tree, and then obviously being sure not to make a circuit. And then you repeat until n-1 edges have been added, or you iterate. And again, this is a property of the spanning tree, right? So the n is the number of vertices here. So n-1 edges have been added. So you build the tree in succession here. All right. Yeah, let's do an example. So I have this image, whoops, which we are going to use twice. So actually I just want to copy it. We'll use this for both of them and make for both algorithms that we're going to use, and then we'll make sure we get them both correct. So, all right, this says to start with an edge of the smallest weight. So if we look at this graph, we have 1, 2, 3 edges that have a weight of 1, right? We can choose any of these 3 to be our starting edge. So let's pick, it doesn't matter. So let's pick this one, CD. And now we're going to make a list over here. So we're going to make a list of our choice in order, and then we're going to describe our edge, and we're going to write down the weight, and at the end we're going to add up all the weights. All right, so our first choice is that we're going to take the edge CD, right? CD, whose weight is 1. And then from CD, we have 1, 2, 3 choices. So we can take the edge CG, DH, or CB. We're going to take the one with the smallest weight, right? So we're going to take CG. So this is choice 2. We're going to take CG, and that has a weight of 2, right? Now from here we have, again, choices, right? So now we have the vertices that are in the tree. So we have now a choice CB is still there, choice of 3. FG is a 3, and DH is a 5. GH is a 3. So we got to pick one of the 3s, right? So we have a 3, 3, 3, or 5. We're going to pick one of the 3s. It doesn't matter which one. All right, so just for the sake of argument, let's say we take FG here. All right, so this will be our third choice. FG, its weight is 3. Now from FG, once we add this, oh, by the way, we had a 4 here, right? Which I didn't mention, but 4 is bigger than 3. So we had a 4 we could have chosen, but we didn't want to choose that anyway. From here, we now have these choices of 1, 2, right? Every time you add an edge, you still have all the previous choices you could have made, but you also have more choices, right? So from here, we probably want to add FB. Now, we're not probably, we do. That's a weight of 1, right? So this is our fourth choice. We add FB, and its weight is 1. And then from there, now we have a 2 here, a 2 here. That's it, right? So we want either this 2 or this 2. And again, doesn't matter. As long as we're not closing off any simple circuits, then we can add either one, right? So step 5, we add FJ. That has a weight of 2. Then we need 2 is still the best, right? From there, if we look at all the weights that are adjacent, so AB is going to be our step number 6, or edge number 6. AB, this is weight 2. By the way, we should have counted the vertices, right? There's 12 vertices in this graph, so we need to get all the way up to 11 edges. So now we have a whole bunch of 3s that we can choose. This one cannot be chosen, right? BC. BC cannot be chosen because that would close a simple circuit. So that one's done. But we have a 3 here, 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 right? So let's just do them one at a time. So AE, that's choice 7. That's a 3, all right? We can go IJ. IJ is better than either of these 4s, right? So we're still 3 is still the best we're going to do. So 8, we have IJ. And that's a 3. And then this, we can use this 3 right here, JK. Change the color. So JK can be the next 3 that we choose. Remember, 4, 5, this 3 is the other choice, right? So this is step 9. We choose JK. 3 on that one. Now we have to choose KL, right? Because KL is the smallest weight. So KL is just weight 1. So this is step 10. There's only one more step to make, right? KL is weight 1. And then we have a 3 or a 3. It doesn't matter. It doesn't matter. You can choose either one. So we'll take this one, HL. Why not? So HL, that's weight 3. Okay, and that fills out everything. So look at what we've ignored in this process. This 5 did not get chosen. This 4, this 4, this 4. None of the 4s got chosen. And then 2 of the 3s didn't get chosen. But we could have made choices to get them chosen, right? But we never would have chosen the 5 or the 2 4s. So let's add all these up and find the total weight here. So the total weight. So this is, by the way, this fills out our entire tree, right? And look at it, it did make a tree. Every vertex is accounted for. Right? Every vertex is accounted for. Yeah, and so it's a tree. So what's this going to be? 6, 7, 9, 11, 14, 17, 20, 24. So there's the total weight, 24. By the way, you know, again, not unique, right? This is not unique. The choice of this was not unique in any way. So I made choices at many different steps of which ones to do first, which ones to add when, right? But we ended up with a graph of weight 24. All right, so there's one more algorithm, and this one is called Kruskal's algorithm. We are on item 6, I guess, unless I miscounted at some point. So this one's Kruskal's algorithm. This one's also for finding minimum spanning trees of weighted graphs. So same deal as before. We have our simple connected weighted graph, and we want to try to find a minimum spanning tree. So it's very, very similar, okay, this algorithm. It's a little bit different. What are we going to do? This time we're going to choose an edge with the smallest weight, same starting point, right? So choose an edge with the minimum weight in the entire graph. Again, if there's a choice, you just pick one of them. And then from there, we add any edge in G. And this is the key. All right, so add any edge. It doesn't have to be incident with the given edges, right? And so add any edge in G to what we'll call our tree, to T, that has the smallest weight and does not form a circuit. So we just look at the edge weights and we pick the smallest ones that don't force us to form a circuit. So with the smallest weight that do not close a circuit. So one at a time, we add edges of the smallest weight. We don't even care how they come together, as long the only thing we care about is that they don't close a circuit. All right? And so step 3 is to obviously continue, not step 3, but part 3 here, continue until n minus 1 edges have been added. All right, let's do the same exact example using Kruskal's algorithm. And so this time, what are we going to do? This time we don't, well, we can okay, my computer froze for a minute. We can still choose CD to be our first one, right? So again, we'll make our list over here of choice. We have to get up to 11, right? The edge, we have to identify it. And the weight is going to be 1 here, right? So our first choice is CD. Oops, choice is just number. This is just number 1. That's what I mean by this. There's going to be 11 of them, right? So our first choice is CD. It has weight 1. Now we want to add in all the other weight ones because they don't close off a circuit, right? So choices 2 and 3 are going to be BF and KL, and they each have weight 1 as well, right? So there we go. That's all the weight 1s. Now we go to weight 2. Well, we can add, just look around for weight 2, right? So we can add all the weight 2s. every edge of weight 2 can be added because none of those are going to force us to close off a circuit, right? So this is going to be our choices 4, 5, and 6. And it's going to be AB. Again, not related to the original edge at all, right? Not connected in any way. FJ. And then CG. And these are all 2s. 2, 2, 2. From there, we go up to the next weight. And now we have to be careful, but we can add in AE, IJ, JK, FG. So far, everything's good. We cannot add BC, right? Because that would close off. That would close off a circuit. We can add GH, and we cannot add HL, but we don't need to. We can add GH, and then we're done, actually, right? So this is adding 7, 8, 9, 10, and 11. So we added, the way I did it was AE, then IJ, then FG, JK, and then GH. And these are all 3s. All right, and then we add these up. We have 15, 6, 3, added up, 24. Same weight, right? Is it the same graph? No, it's different, right? It's a different tree. Again, the real choices I made are FG versus BC, maybe, right? Either one of those could be chosen. GH versus HL, you can change those choices as well. So this is Kruskal's algorithm. You end with this tree. Again, this is a tree. It's hard to look at when it has the black edges still in there. But if you took this thing out and you were to draw it by itself, you could see that very clearly it doesn't have any simple circuits. So this is a minimum spanning tree, and again, minimum only applies when you're talking about a weighted graph. So that's it for this section, this chapter actually. So we'll leave this here, and I'll talk to you guys in the next lecture.